Welcome to this 10-minute explanation of the ESF Floating Network Runtime prototype. The diagram presents a fully computable shared spectral state framework. The goal is to let multiple AI nodes share a common state, evolve it, verify it, and apply it across several domains. In this video, we walk through the architecture from the state pipeline to the network layer, the output layer, and the embedded program structure. The computable state pipeline is the first column of the diagram. It begins with a program object, represented as an abstract syntax tree. The AST is then converted into a Gödel-like integer. This integer is projected into an ATG sequence, which is a symbolic base for string. Finally, the tau function and spectral index transform the result into a coordinate inside the model's spectral space. The shared state is expressed as JSON. This is important because JSON is both human-readable and machine-readable. Every generation can carry its AST label, Gödel-like number, ATG string, tau value, spectral index, protocol version, and timestamp. By using a structured state object, the runtime can become inspectable and reproducible instead of disappearing into a black box. The computable spectral space is the visual heart of the framework. The diagram places the generated state into a plane called lambda. The critical axis, shown at 0.5, is a symbolic organizing line. The spectral index functions as a compact address for the generated state. This is best understood as a formal model space. A way of visualizing the state, not a direct physical claim. The floating network layer turns a single runtime into a distributed architecture. Each AI node receives the shared state, validates it, and updates its own local model. A node may then run inference, or interpretation, and broadcast a new state back to the network. This creates a floating shared spectral state, not locked inside one machine, but circulated among multiple participating nodes. Verification is the difference between a poetic diagram and an engineering prototype. Round-trip checks help ensure that the encoding and decoding pipeline remains coherent. Deterministic formulas make the model reproducible. State history allows the system to be audited, rolled back, and replayed. This is why the diagram emphasizes validation and local update before broadcasting a new state. The application layer shows how the symbolic runtime can be applied. GalaxyDynamics can represent astrophysical simulations or symbolic models of evolving systems. TimeContinuation can represent long-running sequences. ThermodynamicTransitions can model changes between states. SDG 17 analysis suggests that the same encoding pipeline could organize structured reasoning about sustainability and global goals. The output layer is important because a runtime is useful only if its state can be shared. The output may be JSON for machine processing, data analysis for inspection, a presentation for communication, a movie for demonstration, or a report for archiving. This video itself is an example of that output layer. It turns the system into an explainable media artifact. The program you supplied is a compact computable runtime. It starts with a seed S. Each generation computes G by multiplying the seed by 17, adding 7, taking a large modulus, and adding 2. Then it computes tau of G. The spectral index L is computed from G, tau, and the generation number. The output object records the generation, state, applications, and status. The background audio is generated synthetically. It combines a 0-point carrier, where the left and right channels share the same 210 Hz tone, with a subtle gamma-like binaural texture. Metallic modulation and slow spectral motion give it an alien technology atmosphere. This audio is used only as a creative soundtrack. It should not be treated as a medical or therapeutic intervention. This video is encoded as a self-describing artifact. The MP4 metadata includes compressed JSON that describes the state pipeline, formulas, audio design, output layer, and runtime structure. The subtitle file is also embedded as a soft subtitle stream. Therefore, the video is not only an explanation of the floating network runtime, it also carries a compact form of its own structural specification. In summary, the ESF Floating Network Runtime is a computable shared spectral state framework. A state becomes structure. Structure becomes a number. The number becomes an ATGC sequence. Tau and spectral index converted into a coordinate. Multiple nodes can then share, validate, infer, update, and broadcast. The prototype joins computation, visualization, alien tech audio, subtitles, and embedded metadata into one explanatory video.